Hello, I am Thibaut from Université Grenoble-Alpes. With my co-authors, Jocelyne Trocaz, Amélie Rocher-Capellan and François Bérard, we present GeoSuite, General Purpose Interactions for Handed Perspective Cooptic Displays, or HPCDs for short. Here you have an HPCD. The display is held with both hands. The viewpoint on the scene is continuously updated according to the positions of the display and the user. This creates a strong illusion of presence of the virtual objects. Compared to virtual and augmented reality, HPCD offers a smaller field of view, but it seems to provide more comfort and precision, especially when the HPCD is large enough to be held with both hands. While sitting, a two-handed grip favors precise and stable interaction while reducing the fatigue in the arms. This could make HPCDs suitable for applications that require long session and precision, such as 3D modeling. But for this, general-purpose interaction must be designed. VIA HMD usually rely on raycasting to perform general interactions such as widget selection in control panels. With AR HMD, users usually interact directly with their hands through mid-air interactions. These two techniques require the usage of at least one free hand. With large HPCDs, both hands are continuously holding the sphere, so these techniques cannot be reproduced. Previous work on HPCDs has been focused mainly on viewpoint and object control. Our work also relates to recent work in VR that explored the use of a two-handed tangible as input, but here again, this was only for viewpoint and object control. In this work, we want to provide buttons, scales, hierarchical menus and control panels for two-handed HPCDs. We also investigating object selection and scene zooming. Our design process was based on trial and error from informal user feedback during the past 3 years. We also ran a qualitative user evaluation to investigate the usability of the proposed techniques. To do so, we implemented a standalone anatomy learning application. Before presenting our design, I need to introduce some general considerations. During our process, we continuously had to deal with the reality bias versus efficiency trade-off. For instance, to move in a VR environment, you can reproduce the user's physical movement or use non-physical techniques such as teleporting to a selected position. Interactions that are based on reality are usually fast to learn and do not generate too much cognitive load, as they rely on users' physical skills. On the other hand, getting rid of the reality limitations allow experts users to yield higher performances, especially through shortcuts like the teleportation. Commands that require smaller amounts of motor control can also be implemented to perform physically demanding tasks. In our design process, we tend to propose alternatives that either favor intuitiveness or efficiency. I will now introduce our design. We identified two main modes for the spatial relationship between the display and the virtual scene. The scene can be fixed inside the HPCD, like in a snow globe, or it can be fixed in the user environment while the sphere is used as a porthole. We identified that the snow globe allowed natural manipulation of the object, while the porthole was useful to explore large scenes. With the porthole metaphor, we investigated different clipping methods. With full clipping, the HPCD behaves like a container that only displays objects inside its boundaries. By not clipping the scene behind the display, users benefit from a larger contextual understanding of the scene without the need to push the HPCD far from their resting pose. As this gain of efficiency did not come with a loss of intuitiveness, we implemented this solution. All of the interactions that we designed involve a cursor. We used a 3D cross rigidly attached at the center of the sphere. In direct pointing, users move the pointer inside the object. They validate this selection. The object is then rigidly attached to the display and can be transformed with 6 degrees of freedom. We tested two alternatives for the activation, either a tap on the ground with a feet or a tap on the HPCD surface with a finger. Foot controls are a common practice for surgeons who cannot use their hands outside of their sterile walking area. In addition, foot controls induce no parasitic motion of the upper limbs, but they are not suitable for mobile usage. On the other hand, tapping on the display with the index is very efficient. With the stability provided by the two-handed grip, we observe no parasitic motion induced by index taps. We chose the alternative as it seems more suitable for future, more mobile HPCDs. Here you can see a user selecting and moving objects. Although it seems quite natural to move the cursor inside the object, we observed several missed selections from novice users, as they did not push the cursor all the way into the target. We have two hypotheses that could contribute to explaining this behavior. It could be due to a bad depth perception or to users voluntarily stopping their motion in front of the target while expecting to be able to pick the object behind the cursor, like in most desktop applications. Either way, misselection completely disappears after a short user training when using a feedback that indicates when objects are selectable. Still, this observation highlights the need for selection methods which allow far object selection while minimizing the needed movement. We implemented a picking method inspired by raycasting. Users align the pointer with a distant object which becomes pre-selected with an outline. To manipulate the object, if we directly attach it to the display, it introduced an unsuitable lever arm effect, causing the object to quickly disappear from the display. To alleviate this problem, we designed two different pointer behavior. With the proxy cursor, the pointer jumps to the object. From then on, the transformation on the display are reproduced on the cursor and the object. With the magnet cursor, it is the object that jumps to the cursor on validation, like if the user used the tractor beam to fetch it. It can then be manipulated as if it was selected by direct pointing. Here we show the magnet cursor on the actual system. Because the cursor is inside the scene, objects in front of the cursor can also be selected. As a result, direct pointing can be seen as a particular case of the magnet cursor, so we combine them with no need for a mode switch. We tested display rotation for scalar parameter control. The yaw and roll rotation only affords small rotation and suffer from occlusion from the hands and forearms. Each afford much larger rotation with no occlusion. We use the pitch to control the zoom factor of the scene, while translation can be used to continuously update the zoom center without interfering with the rotations. This way, both rotations and translation can be controlled simultaneously to handle a continuous zooming interaction. Here, we illustrate how this interaction is both intuitive and efficient. We recommend to combine rotation only to handle an integral control, like the 3D orientation of an explored object. We tested the control of non-integral commands from two distinct rotations. For instance, the roll can be used to select a mean value of a range slider, while the pitch is used to control the width of the range. This interaction proved difficult for novice users and was prone to engender parasitic motion in between the two control parameters. For commands, we designed two alternatives, a marking menu focused on efficiency and a control panel focused on intuitiveness. We built a marking menu that pops up in front of the user after a double tap of the index. We show a menu pointer at the intersection of the menu and the eye cursor ray. The menu is fixed in the physical world. By moving the display, user moves the menu pointer and makes their selection with crossings. Here we show a two-level marking menu that triggers standard views. Marking menus allow for very efficient command activation, especially for expert users. The menu inner radius is small so as to minimize the required movements. We also designed a control panel. This one remains attached to the eye cursor ray. User interact with the panel thanks to a rod that is attached to the display. By rotating the display, users activate controls by crossing them with the rod. Attaching the panel on the rod to the display allows it to be operated independently from the display translation. We design radial widgets to be integrated within the control panel. To limit the need for finger taps, buttons are automatically validated after a dwell delay of half a second. We provide a continuous feedback by the form of a blue progress bar all around the widgets to enhance users' understanding of the widget behavior. Crossing interaction have been shown to be very effective for sliders. With a large widget, the rod can either remain close to the inner radius for a fast control or goes near the outer radius to enhance accuracy. Once the value has been picked, users must move the rod out of the widget to stop changing it. When precise values must be picked, users can also tap to close the menu while validating the current value. Here we show how a slider on the panel can be used to control a zoom factor while the scene is being explored by display translations. As you can see, widgets' inner radiuses are quite big in order to limit misactivation. The menu remains on top of the scene during the zoom control for more feedback consistency. Indeed, in this design we focused on the interaction intuitiveness. Now we show the exploration of the commands of a two-level radial menu. The leaves of the menu are only activated after a dwell delay. We designed an anatomy learning application to illustrate how the general-purpose interaction presented can be instantiated in a standalone application. We chose this application as VR and AR were identified as having great potential for medical learning, but remains underexploited due to technical limitations. The application consisted in a series of docking tasks where anatomical parts have to be docked into a target leg. We focused on intuitiveness when designing this application, as it was intended for limited usage from novice users. Before docking a part, users had to choose the right one. We implemented two choosing alternatives. With a minute cursor, users pick the chosen part among all parts set on the side of the leg. With the radial menu, users choose the part from the names of the menu commands. With both alternatives, users could handle the scene scale at will from a crossing slider in the menu. This interaction was very useful as some parts were a lot smaller than others. It also allowed to test both the zoom and the sliders. We welcomed 8 participants for a qualitative user evaluation. Participants had no experience with the evaluated interaction nor prior anatomy knowledge. We launched the application and only told them that they could interact with the sphere by moving, rotating, tapping, and double tapping, and that the application was related to anatomy learning. They had to discover the interaction by themselves. In less than 3 minutes, all participants discovered and understood all the interactions, showing the intuitiveness of the interface. It seems that interacting through objects that felt physically present in the scene, like the cursor and the rod, played a fundamental role in the discoverability of this interface. We observed a lot of physical behaviors that participants would have performed instinctively in a similar situation in their everyday life. They were moving around the sphere to change their viewpoint or leaning forward to get a closer look. One participant claimed, "The magnet cursor is acting like any science fiction tractor beam. It feels strangely natural and satisfying to use. This could be the result of a halo effect of the most physical interactions onto the less physical one." Usually, participants did not experience muscular fatigue, except for 2 participants who were holding the sphere quite high. This highlights the importance of having a good posture to reduce the gorilla arm effect. In the end, all participants found all the testing interaction intuitive and efficient, which is a good sign for the acceptability of HPCDs. Thank you for watching.